Hello everyone, and welcome to the Equation Web. Today we'll be doing another arithmetic problem like we have done before. So let's start with the question. So today's question will focus a lot on prime factors because it is a proof and you just need to prove something that is related to prime factorization and stuff like that. So today's question is, prove that there are infinitely many positive integers n such that the number n to the fourth plus 1 has a prime divisor greater than 2n. I'll give you guys some time to do this question and solve it out yourself. So firstly, we can use an identity that is really similar to n to the fourth plus 1. And we can say that n squared plus 1 squared minus n squared is equal to n squared minus n plus 1 times n squared plus n plus 1. Now, if we multiply out n squared plus 1 squared, we get n to the fourth plus 2n squared plus 1. Then you have to subtract n squared from it, so we get n to the fourth plus n squared plus 1. And then we get that the two expressions right there multiplied are equal to n to the fourth plus n squared plus 1, since n squared minus n plus 1 times n squared plus n plus 1 is the difference of squares formula. So then we can plug in n plus 1 into our first quadratic factor, which was n squared minus n plus 1. If we plug that in, we get n plus 1 squared minus n plus 1 plus 1. If we multiply out n plus 1 squared, we get n squared plus 2n plus 1. Then we subtract n plus 1 from that, and then add 1. From this, we can simplify and get that this whole, if we just plug in n plus 1 into that quadratic term, we get n squared plus n plus 1. And that was our other quadratic term. So this will be really helpful for us later on. So since we plugged in n plus 1 into that term and we got n squared plus n plus 1, we can write them as a sequence of two terms. First, we get a of n is equal to n squared plus n plus 1. Then we can write n squared minus n plus 1 as a of n minus 1 because of what we did previously. Then we can just plug in a of n and a of n minus 1 into our previous factored form, and we get that n to the fourth plus n squared plus 1 is equal to a of n times a of n minus 1. Let's say that p is a prime divisor of n squared plus n plus 1. Since it divides n squared plus n plus 1, it also divides the larger product that we had previously. Now, let's say that p divides n. If p divides n, that means that p must also divide 1, and that is impossible. So, the greatest common factor of p and n is 1. Since n squared plus n plus 1 grows quadratically, its largest prime factor must eventually break a linear boundary. Now let's contradict that p is less than or equal to 2n. If we choose values where n squared plus n plus 1 is prime, then p will be close to or exactly that number. Since n squared plus n plus 1 is greater than 2n for when n is greater than or equal to 1, the prime divisor will be greater than 2n. Proving this proves that n to the fourth plus 1 will also have a prime divisor that is always greater than 2n. Our question was, prove that there are infinitely many positive integers n such that the number n to the fourth plus 1 has a prime divisor greater than 2n. We have just proved this. Thank you for watching, and make sure to like and subscribe.